Alright, we're ready for 9-2 wave properties. So now we've talked about a transverse versus a longitudinal wave, so now we're ready to get into the actual wave properties. We're also going to get into 9-3 with this video because 9-3 is super short, so we're just going to kind of shove the two videos into one. So just be prepared that at the very end you'll see 9-3 as well. So here we go. Alright. First of all, we're going to dissect a wave in general and talk about all the different properties of a wave. So first thing we're going to look at is with a wave itself, and so we have a transverse wave here. We're going to look at when you have a transverse wave, or a wave in general, when you have a distance from basically like hilltop to hilltop, or even valley to valley. And another term that we use here in physics, we call it crest to crest or trough to trough. Those are called wavelengths. Okay? And so that's the distance between one point on a wave to the nearest point just like it. Okay, so that's a wavelength. So crest to crest, trough to trough. So this here is a wavelength. If we kept going like down here, that would be a wavelength. Okay. Notice that here, this person holding this nice little rope right here, want to point out just right here. Notice that this line where it cuts through, they pointed out that that's called the rest position. Okay, so just to kind of make note of that. Alright, so the first thing we want to point out that that's the wavelength. And you'll see later on, just in case, wavelength is abbreviated because we use a lot of Greek symbols. Wavelength is abbreviated with the Greek symbol lambda, and so it looks like an upside down Y. We'll get to this a little bit more, but just so I kind of introduce it now. So it looks like, oh, I can't write up there for some reason. Oh, it's coming. Sorry. Here, I'll write down here in the white again. So my computer is responding very, very slow now all of a sudden. Maybe if I just pause for a second. Okay. Try again. Here we go. It'll show up here. There. So look, it looks like an upside down Y, so that's a lambda. Okay? Alright, so next up, frequency. So frequency is just the number of wavelengths that pass a fixed point each second. So we have that wavelength that we just looked at. So you have, you have a wavelength. So and of course, my drawings are absolutely horrible. It's even worse when I'm trying to draw on a computer. So you have this wavelength that's horrible, but it's going up and down, up and down, and up and down. And it's like, well, how many wavelengths? So there's one, there's two, and there would technically be three. How many are happening in this particular given point in time? Or how many are happening in a second? So let's say that this is 1 second. Well, there's three happening in this second. So its frequency would be 3. So 3 wavelengths per second, or its frequency would be 3 hertz. Because frequency is expressed in hertz. So it's just the number of wavelengths that happen per second. So frequency is just the number of wavelengths that happen per second. So if we were looking at so many seconds, maybe it would be 6, if it was double that. Frequency is abbreviated with kind of like a fancy V. You do a V and with a little line attached to it. Okay, so that's frequency. And then, like I said, the units for it are hertz. I know, it hurts. Yeah. And hertz are abbreviated HZ, capital H, lowercase z. So what's the relationship? It kind of makes sense that as your frequency goes up, so the more of these little, the more of the up and downs you get, the wavelength gets smaller. Because you think about it, if you have this cycle, this time, the number of little up and down, the number of bumps that you get has to be shorter. So frequency goes up, wavelength goes down. How fast does a wave go? Well, the speed of the wave depends on what you're putting it through. It depends on your medium. Sound usually travels faster through liquids and solids than it does through gases. It likes to travel through things. It likes to go through things. So it likes to have things to bounce off of. Light, however, likes to go through nothing. It likes to go through a vacuum or even gases. Light likes to not have anything to travel through. Sound, going back to that again, likes to travel through warmer materials than cooler materials. So there's a couple things about sound versus light. We'll talk a little bit more about wave speed too, as far as like the speed of, well, we're going to do some calculations with that, but a little bit more about the speed of a particular wave later. Speaking of the speed of a wave and how to calculate it though, okay, so, and that's why I wanted to introduce what like frequency and wavelength, what their symbols look like. Well, and in fact here they use F for frequency instead to kind of not scare you off. I don't really like that because that's kind of, I don't know, I don't use that. But so speed is equal to the frequency of a wave times its wavelength. Okay, so that's your equation. And so speed, of course, speed's always in meters per second, just like we did at the beginning of the year, right? Speed is distance divided by time, so speed is your meters per second. Your frequency is your hertz. Because think about it, frequency is the number of waves per second, so the number of meters per second. Well, actually 1 per second, sorry. And then wavelength is in meters, so that's how you get the units meters per second. Okay, so let's just look at an example. It'll make more sense. So we have our equation is V equals, I'll just use this one so it probably doesn't confuse you as much. F equals, or V equals F lambda. So our V, F, lambda. So V, remember, stands for our velocity or speed in meters per second. Our F stands for our frequency, and that's in hertz. And our lambda stands for our wavelength, which is going to be in meters. Okay? So they give us in this problem, they give us a wave traveling in water has a frequency of 250 hertz and a wavelength of 6 meters. What is the speed of the wave? Okay, so 250 hertz, so they give us the frequency, a wavelength of 6 meters. So notice that the only thing we don't have is that velocity, aka, I guess I should write this up here, speed. So look, you're going to take V equals 250 times 6. So that's going to be equal to 1,500, and then you just label it meters per second because it is solving for V, which is your speed. Okay. Now, let's try another one, because of course that's just doing straight multiplication. If you're solving for either of the other two variables, so if you're solving for, I'll write the equation down again, V equals F lambda. So if you're solving for F or lambda, it's going to be a division problem. So the only time you multiply is if you're solving for V. So we have V, we have F, we have lambda. So like this one, the lowest pitch sounds humans can generally hear have a frequency of 20 hertz. What is the approximate wavelength of these sound waves if their wave speed is 340 meters per second? Okay, so 20 hertz, so hertz is a frequency. Wave speed, 340 meters per second, so they're giving you the speed or the velocity. Find lambda. Because they're even saying what is the approximate wavelength. So this one you have 340 is equal to 20 times lambda. So this is a straight division problem. So 340 divided by 20 is 17. So lambda is equal to 17, And if you're solving for lambda, it is meters, because that's your wavelength. Okay, so there is a couple examples. So if you were solving for frequency, you would do the same exact thing, except for you would label it in hertz. Right. Okay, a couple of the things talking about these waves and how to label things. We already talked about if you go from crest to crest. Okay, and it's even labeled here. If you go from crest, notice that they're labeling this right here a crest, that's a wavelength. Or if you go from trough to trough, that is a wavelength. And notice again, it's labeled right here, trough, and it's labeled here, crest. There's some things to identify as far as a wave goes. And we already talked about this is the rest position. And of course, you need to be able to identify all these pieces of a transverse wave. Now, something else you need to identify, the height of a particular wave is called the amplitude. So, the height of this particular wave, that's that amplitude. So, they call the amplitude the amount of the disturbance from a wave. So, the greater the wave's amplitude is, the greater the disturbance the waves produce. So, basically the higher it is, the more the amplitude is. Easy enough. Okay, and like I said, here is 9.3. I'm just throwing this at the end because 9.3 is super short. There's just a couple of basic vocab words that we need to learn from 9.3. Like, for example, we need to learn the word reflection. It just basically is when an object strikes an object, or a wave strikes, I can't talk, when a wave strikes an object and it bounces off. Okay? All types of waves can be reflected. The most common thing you probably think of when you think of reflected is an echo. Maybe even like when you look in a mirror, you see your reflection. Okay, so sound, water, light, those can all be reflected. Then we have something called refraction. This is the bending of light caused by a change of speed from one medium to another. So light waves travel, like for example, slower in water than air. So for example, if you put light, shine a flashlight in air, and then when it goes down in water, it gets refracted. And so instead of going in the straight downward path, it actually refracts down because it's moving slower, so it bends. I have another example, a picture of this on the next slide. Where it's showing you where it's going the opposite direction if you were to shine the light up. Oops. I don't know what I just did. Hopefully nothing bad. Oh, there we go. Where you shine it upwards, same thing. It's going at a slower pace, and then it's going to get reflected this one because it's going to speed up when it goes out of the water. So instead of going this way, it's going to bend that way. It's because of refraction, too, that we have to be very careful when we go swimming, for example. When we look down, we think that objects are straight down. So, like when we look at somebody that's in a pool, we think that they are like closer than what they really are. So, excuse me. For example, we think that this gentleman is right here in the pool. But because of refraction, he is actually lower in the pool than what we think. And so we have to be really careful about, what we're doing, because that can be really dangerous about where we think he is versus where he is, and and that's because our brain isn't able to process that refraction process. So it's kind of interesting that our brain, our eyes do the same process, and that's because of the whole light travels and it bends, and so it's kind of interesting. So, and that's the end of section 2 and 3.